Thank you for inviting me. So today I'm going to talk about an overview of complex unit gain graphs and their spectra. Well, so this is the outline. So first, I'll give a very short introduction of what is complex unit gain graphs. And then I'll present some result on spectrum and spectral radius of T gain graph or complex unit gain graph. And then I'll give some bounds of energy of T gain graph. And finally, I'll give a brief introduction of gain distance matrices. Well, so as we know that in spectral graph theory, mostly we utilize combinatorial and structural properties of a graph in terms of their associated matrix properties and vice versa. So in the beginning, spectral graph theory deals with only undirected graph, but later researcher got interested to study spectral properties of sine graph, oriented graph, mixed graph digraphs instead of undirected graph. So here we consider another class of graphs, which is complex unit gain graphs or T gain graphs. So T gain graphs not only generalizes all such well-known graphs, but also it has its own distinct meaning due to its combinatorial and spectral features. So in this seminar, mainly we focus on some result of complex unit gain graphs and their spectra. Well, so before going to T gain graph or complex unit gain graph, we need to know about what is gain graph or G gain graph. So Jaslavsky in 1989 introduced the concept of gain graph or G gain graph, where G is a multiplicative group. So let us recall some known notation. So suppose this G be a simple graph and its vertex set V of G, it is labeled by V1, V2 up to Vn, and its edge set E of G. Now, an undirected edge between the vertices Vi and Vj, it is denoted by Ei, J. And then oriented edge from the vertex Vi to Vj, it is here I'm denoting Ei, J arrow. Now, each undirected edge that can be thought of as a pair of opposite oriented edges. So the collections of all such pair of opposite oriented edges, this is known as the directed edge set of a graph capital G, and it is here I'm denoting by like E arrow G. Okay. Now a G gain graph or a gain graph on a simple graph capital G, this is a graph, okay, such that for each edge, if one orientation assign a value, let's say small s, coming from the multiplicative group G, then the value of the reverse orientation, that would be S inverse, which is nothing but the multiplicative inverse of S. Suppose we assign that, assume that this function phi, this let us call this assignment by phi. Then this phi is known as a gain function. So gain function, basically, this is a mapping from directed edge set to multiplicative group G. Okay. Now later in 2011, Rep considered a particular choice of G. He assumed G to be a unit circle, call it like T, and then put forward the concept of T gain graph. So what is T gain graph here? So a T gain graph or a complex unit gain graph on an underlying graph capital G, this is basically a graph G together with a gain function phi, okay, such that for each edge, the gain of any orientation is nothing but the complex conjugate of the gain of the reverse orientation. Okay. And it is denoted by this pair G, phi. This phi, this is basically a gain function. Okay. Now some basic definition. So the gain of a cycle. Suppose C, this is a cycle and its consecutive vertices are V1, V2, VL, and V1. Then the gain of this cycle in this particular orientation, which is nothing but the product of the gain of its oriented edges in this cycle, in that particular orientation. Now, a cycle C, this is called neutral if its gain is 1, and a gain graph is said to be balanced if its all cycles are neutral. Now, a function from vertex set of G to complex a vertex set of G to T is known as switching function. Now, we consider two T gain graph, let's say phi 1 and phi 2 on the same underlying graph G, then they are said to be switching equivalent and denoted by this symbol phi 1 switching equivalent to phi 2 if there is a switching function, let's say eta, such that one can be achieved from other through this switching function by this relation. Okay. Now, the adjacency matrix of a T gain graph that can be defined in this way. So this is a Hermitian matrix, Hermitian n cross n matrix, and its diagonals are 0. And its ijth entries is nothing but the gain of the oriented edge and orientations from the vertex Vi to Vj, and 0 otherwise. Now, the set of all eigenvalues of the adjacency matrix of phi, this is known as the spectrum of phi, and this is a multiset, obviously. So this, and it is denoted by spec of phi. And the energy of a T gain graph phi, which is nothing but the sum of the absolute values of all eigenvalues of phi. Okay, now in one example, suppose G, this is an underlining graph or a simple graph. And here it is one T gain graph phi 1. So in this T gain graph phi 1, we can see in this orientation, our gain is iota. Therefore, the reverse orientation gain is minus iota. Now here we have another T gain graph phi 2. So here we can see in this orientation, it is some different e to the power I pi by 3. Okay. So now if we change the gain of its edges, then we have uncountable many T gain graph associated with a particular structure G. So instead of considering the spectral properties of G, here we will consider these uncountable many collections of graphs, and then we see how they are related to the structure of its undirected graph G. So this is the adjacency matrices of phi 1 and phi 2. For an example, here we can see the 1, 2 entry of A of phi 1. This is iota, which is nothing but the gain of the edges from the vertex 1 to 2 in this orientation iota, and so on. Now, some other known class of graphs, a sine graph, as we know that this is a graph such that the sign of each of its edges is assigned by either +1 or -1. And its associated adjacency matrix, this is a symmetric matrix, and its diagonals are 0 and non-zero entries are coming from the set +1 or -1. Now, another class of graph, this is a mixed graph. So a mixed graph, this is a graph such that each of its edges is either directed or undirected. So different type of matrices can be associated with a mixed graph. So one of them is Hermitian adjacency matrix. So the Hermitian adjacency matrix, it is denoted by H of X. It is a Hermitian matrix, and its diagonals are 0 and non-zero entries coming from the set 1, ± iota. Later, Mohr introduced another class of matrix, which is new kind of Hermitian adjacency matrix, which is n alpha x. If our X means mixed graph is a simple graph, then we can see this is a Hermitian matrix and its diagonals are 0 and non-zero entries are coming from the set 1, alpha, where this alpha, it is of modulus 1 and its real part is greater than is equal to 0. Now, a particular type of mixed graph is known as oriented graph if its all edges are directed. Well, so in one pictorial view, we can see for a simple graph G, we have uncountable many collections of T gain graph. Among them, we have a finite collection of mixed graph, a unique undirected graph, and finite collections of signed graph. So from this point of view, we can say T gain graph generalizes all such well-known graphs. Well, in this section, I will discuss some some results on spectrum and spectral radius of T-gain graphs in connection with their structural, combinatorial, and spectral properties. So some result on spectrum. So Jaslavsky in 1989 proved that if a gain graph phi is balanced, if and only if phi is switching equivalent to the underlying graph. That is basically g comma 1. Here our gain is 1, means we are taking the gain of all edges are 1. So that is basically the underlying graph. Anyways. Later, Ref in 2011 proved that suppose phi 1 and phi 2 be to T gain graph. If phi 1 is switching equivalent to phi 2, then we can see that imply they have the same spectrum. Now, combining these two results, we get if a T gain graph phi is balanced, that imply the spectrum of phi is same as the spectrum of its underlying graph G. Later, Liuli prove these results for a mixed graph X. So if X is balanced, that imply they have a same spectrum with its underlying graph G. Now the question is, what about its converse? So here is the result. So let phi be a connected T-gain graph, then the spectrum of phi is same as the spectrum of its underlying graph G if and only phi is balanced. So if phi is balanced, then they have same spectrum. That is easy to understand. Now they're converse. So here is the sketch of the proof. So to prove this result, we need one key lemma. It says that let phi be a connected T-gain graph, then the spectral radius of phi is always less than is equal to the spectral radius of its underlying graph G. And equality occurs if and only if either phi or minus phi is balanced. We need another lemma. Let phi be a connected T-gain graph. If our structure is bipartite, then whenever phi is balanced, always imply minus phi is balanced. Now, using these two results, we can easily conclude our statement. So suppose the spectral radius of phi is same as the spectral radius of underlying graph G, that imply, spectrum is same, that imply they have the same spectral radius. Then from lemma 1, we can see either phi is balanced or minus phi is balanced. If phi is balanced, then we are done. If minus phi is balanced, then from the definition, it says that the spectrum of minus A of G is same as the spectrum of A of phi. And since the spectrum of A of phi, that means the spectrum of phi is same as the spectrum of G. So that imply the spectrum of minus A of G is same as the spectrum of A of G. A of G means adjacency matrix of the graph G. Anyways, that means G, the underlying graph G, the spectrum of the underlying graph G is symmetric about origin. Therefore, we know our structure is bipartite. Right. So now our structure is bipartite and minus phi is balanced. Therefore, from lemma 2, it's imply phi is minus of minus phi is balanced. So phi is balanced. Therefore, this is the result. Well, now another result on spectrum. Well, so let phi 1, again recall this result. Let phi 1 is switching equivalent to phi 2, that imply they have the same spectrum. However, this result need not be true in general. So here we have one example. Let phi 1 and phi 2 be to T-gain graph on the structure C3, means a cycle with 3 vertices. Then we can see here phi 1 is not switching equivalent to phi 2. However, they have the same spectrum. So for arbitrary phi 1 and phi 2, we are not able to get the converse of this statement. Okay. So in this direction, we have one result. Let phi be a T-gain graph, then following are equivalent. If our structure is tree, if and only if, for any two T-gain graph phi 1 and phi 2 on G, they have the same spectrum. If and only if, for any two T-gain graph phi 1 and phi 2 on G, they have the same spectral radius. Now, result on bipartite graphs. So for the case of simple graph, we know that a simple graph G is bipartite if and only if its spectrum is symmetric about origin. However, for the case of T-gain graph, this need not be true. One side is okay, means if phi is a bipartite T-gain graph, then its spectrum is symmetric about origin. So here the converse is not true. So here we have one example. So in this example, we can see that the spectrum is symmetric about origin. However, its structure is not bipartite. So to make converse true, we need one additional condition. So here is the condition. So here phi be a T-gain graph and its eigenvalues with eigenvalues of phi are symmetric about origin. And if this happens, then we can say our structure is bipartite. Well, another result. So let phi be a connected T-gain graph. If G is bipartite, if and only if equality of spectral radius implies equality of spectrum with its underlying graph G for every T-gain graph phi. Now, bipartite graphs with exactly one positive eigenvalues. So for a connected bipartite graph G, we know that G has exactly one positive eigenvalue if and only if G is a complete bipartite graph. However, if we consider T-gain graph, then it is not true for arbitrary connected bipartite T-gain graph. So here is one example. So in this example, we can see that our structure is a complete bipartite T-gain graph. However, if we look into its spectrum, we can see it has two positive eigenvalues. So how we can get the result? So here is the result. So let phi be any connected, let phi be any T-gain graph on a connected bipartite graph G. Then phi has exactly one positive eigenvalue if and only if phi is a balanced complete bipartite T-gain graph. So we must have to take the balancedness of this T-gain graph phi. Otherwise, if we take any arbitrary T-gain graph on this structure, then we can't get the converse. Means we can't have the exactly one positive eigenvalue. Well, now Ref in 2011 proved that let phi 1 and phi 2 be two connected T-gain graph. Then if phi 1 and phi 2 preserve their gain over all cycle C, then it's guaranteed that they have the same spectrum. Now, no need to consider all cycles of a graph. If we consider a certain number of cycles that guarantee that they have the same spectrum. So our next results is about that. Let phi 1 and phi 2 be two connected T-gain graph. If phi 1 and phi 2 preserve their gain over all fundamental cycles with respect to some normal spanning tree of G, then they have the same spectrum. So here we are taking normal spanning tree. We are not taking any arbitrary spanning tree. So we are taking normal spanning tree because to get a suitable orientations in the graph. Well, so one of the corollary of this result. So if phi 1 and phi 2 be two connected T-gain graph on a same structure G, then phi 1 is switching equivalent to phi 2 if and only if phi 1 and phi 2 preserve their gain over all fundamental cycles with respect to some normal spanning tree. That would be helpful to prove some of the main result in this section. Anyways, now we come to one such type result for the characteristic polynomial of T-gain graph. So this is the characteristic polynomial of phi. Then we can express its coefficients in this form. So here Hij, this is the set of all elementary subgraph of G with I number of vertices. So if H is a elementary subgraph with I number of vertices, then P of H, this is the number of component in H, and this small c of H, this is the number of cycles in H, and this capital C of H, this is the collections of all cycles in H. Well, now we take two T-gain graph phi1 and phi2 on the same structure G. If phi1 if phi1 and phi2 preserve the real part of their gain over all cycle C, then from this expression we can see this part, this section, I mean this part will be same for both phi1 and phi2, and since their structure is same, so this part will also be same for both phi1 and phi2. Therefore, they have the same characteristic polynomial, so they have the same spectrum. Now, what about converse? So converse need not be true. Here we have one example. Here we are taking G as our underlying graph and phi1 and phi2 be to T-gain graph. So we can see phi1 and phi2 have the same spectrum. However, if we only look into this cycle C1, then for the T-gain graph phi1, we can see here the gain of this C1 is e to the power I pi by 3. And here the gain of this C1 is I. So their real part is different. So the spectrum is same, however, their real part is different. Okay. So therefore, the question is like, for which structure the converse will be true? Now we look into the structure. That means for this structure, the converse is not true. Therefore, we consider some particular type of structure for which the converse will be true. So here we construct two structure. One is Sn. So the construction of Sn is like this. So a class of all connected graph G with n vertices such that for each k and k lie between 3 to n, G has at most one cycle of length k. This is some typical example of a graph in S10. So this is G1 and G2. And now another class of graph, which is Cn, P. So how we can construct it? First, we take a star with n pendant vertices and n copies of a unicyclic graph U of cycle length P. Then we obtain a graph by identifying each pendant vertices of the star with a vertex V of U. And the collections of such graphs is denoted by Cn, P. So one typical figure is like this. So here we can see we are taking a star with 3 pendant vertices and 3 copies of the unicyclic graph. Well, now this is the result. Let phi1 and phi2 be two T-gain graphs on G, where G is any graph coming from this collection. Then phi1 and phi2 have the same spectrum if and only if phi1 and phi2 preserve their real part over all cycles. Means here the spectrum is determined by their cycle gain. Okay, now we come to spectral radius. So here we recall 3 known class of matrices. One is adjacency matrix, another is Hermitian adjacency matrix, and new kind of Hermitian adjacency matrix. Well, so Perron-Frobenius theorem, we know that the spectral radius of a graph is same as the largest eigenvalue. But if we consider any mixed graph, then this is not the case. But surprisingly, Crystal, Gu, and Bojan-Mohor, they prove that the spectral radius of a Hermitian adjacency matrix, I mean spectral radius of X, that means the spectral radius of Hermitian adjacency matrix of X. Well, so the spectral radius of X, they lie within λ1 and 3 times λ1. Okay. Later, Mohor proved these results for a bigger class of matrices in alpha X. Now the question is it possible to extend the above results for any T-gain graph? Now the answer is no. Here we have one example. So this is our structure K5, means a complete graph with 5 number of vertices. Then its largest eigenvalues is 1. However, its spectral radius is 4, which is strictly greater than 3 times λ1. Now, if we look into the proof of this result, we can see the real part of the entries of these matrices are non-negative, and that play a crucial role of proving this result. However, when we consider any T-gain graph, then the entries of their associated adjacency matrix, there the real part may not be positive on may not be non-negative always. We can have sometimes negative also. Okay, so that is a problem. That's why it is not possible to extend these results for arbitrary T-gain graph. However, we construct some class of graphs for which it is possible. So one such construction is, we call it as F graph. Okay, and then we establish the above results for any T-gain graph phi on an F graph. So what is F graph? So the construction of F graph. So first we define a fundamental subgraph. So a fundamental subgraph of a connected graph, let's say G, is a component of a graph G prime. So what is G prime? G prime is obtained from G by after deleting its all bridges, cartages. Okay, let G1 and G2 be to subgraph of a labeled graph G. Then G1 plus G2, which is nothing but the union of G1 plus G2. Okay. Well, now this is F graph. So a connected graph G is called an F graph if for every fundamental cycle there is a sequence of all for every fundamental subgraph, if there is a sequence of all fundamental cycles with respect to some normal spanning tree, let's say this is the sequence CR1, CR2, CRS, such that this inequality holds for all I. Well, if we consider any collection of fundamental cycles, then this inequality, this value is always greater than is equal to 1. So here basically we are skipping the equality 1 condition. So we are only taking strictly greater than 1. Okay. So then we can say that this graph G is an F graph. Okay. So anyways, so now some typical example of F graph. So these are two examples of F graph. So this is a fundamental subgraph and this is another fundamental subgraph. Well, and this is the result. Now let phi be any T-gain graph on an F graph G. Then the spectral radius of phi lie within lambda1 and 3 times lambda1. Now some corollary of it. Suppose our structure is a vertex disjoint cycles. Graph is a vertex disjoint cycle, then the result holds. Suppose our structure means G obtained by subdivisions of each edge of some connected graph, then also result holds. And here also it is, I mean, if we consider K4 as our underlying structure, then also result hold. So there are many graphs. We can prove that the result hold if it is a F graph, if it is an F graph anyways. Now another spectral bounds in terms of largest vertex degree. So here, first we define a Hermitian matrix, which is known as K generalized Hermitian adjacency matrix. So a K generalized Hermitian adjacency matrix of a mixed graph X, it is denoted by HKX. How we can define this? If there is an undirected edge between the vertices VS and VD, then the STth entry will be 1. If the direction is from VS to VD, then the entry will be STth entry will be e to the power iota theta, and if from VT to VS, then it is e to the power minus I theta and 0 otherwise. Here theta is pi by K plus 1. Now, if we take K is equal to 1, we get H1X, and which is nothing but well-known Hermitian adjacency matrix of a mixed graph X, and which is introduced by independently Guo and Mohr and Liu and Li independently. Anyways, and when we take K is equal to 2, then we get H2X, and which is also a known matrix introduced known as Hermitian adjacency matrix of second kind, and it is introduced by Mohr. Now here is the result. So Ref in 2011 proved that for any T-gain graph phi, spectral radius of phi is always less than is equal to delta, means the largest vertex degree of its underlying graph. Later, Guo and Mohr proved that for any mixed graph X, spectral radius of X is less than is equal to delta. And they characterize the structure of a mixed graph X for which equality occurs. Later, Lee et al. They extend these results for, they prove these results for Hermitian, second Hermitian adjacency matrix of second kind. So the spectral radius of H2X is less than is equal to the largest vertex degree, and characterize the structure of a mixed graph for which equality occurs. Well, so our first result is about characterizing equality of Ref's bound. So let phi be any t-gain graph on a connected graph G. Then the spectral radius of phi is equal to the largest vertex degree if and only if our structure is delta regular and either phi or minus phi is balanced. And our second result is about to extend these bounds for K generalized Hermitian adjacency matrix. Because K generalized Hermitian adjacency matrix, this is generalizing, this matrix generalize this Hermitian adjacency matrix and the second kind of Hermitian adjacency matrix. So this is the result. So the spectral radius of HKX, which is less than is equal to delta, and equality occurs if the structure of a mixed graph is either structure A or structure B. So what is structure A and structure B? Let's come to this picture. So here we can see, one geometrical view I present here. So these all boxes, they are the partitions of vertices, okay? And this black line, they are undirected edge, and the dotted red line, they are directed edge. So if any two vertices are there and they are connected by an edge, then they will be undirected. And if there, for example, if one vertex from here to here is connected, then they will be connected by an directed edge, and direction will be in this way, right? So, okay. And similarly for here also. Okay, means here we can see any two vertices of this partition, there is no edge, and so on. Okay. Well, now in this section, we will see, we'll show some, here we establish some energy bounds for t-gain graphs using vertex energy. Okay. So Arichmendi et al. Introduced the notion of vertex energy for simple graph. So energy, vertex energy of simple graphs. So here we define this for t-gain graph. So the energy of a vertex Vi of a t-gain graph phi, this is nothing but the ith diagonal entries of mod of A of phi. So since since A of phi and A of phi star, they are positive semi-definite, so the square root is possible. So that's why we are taking the ith diagonal entries of this matrix as the energy of the vertex Vi. Then we can easily see that the energy of an original t-gain graph phi, that can be expressed as the sum of the energy of its vertices. So what do we do first? We first get the bound of the energy of its vertices, and from there we get some nice energy bound of the graph phi. So the first bound, so the energy of the vertex Vi is greater than or is equal to, so here we are taking that the structure is connected with at least one edge. Then the energy of the vertex Vi is greater than is equal to the degree of the vertex Vi divided by the largest vertex degree. And equality occurs if and only if the t-gain graph phi is switching equivalent to a complete balanced bipartite graph together with the same partition size delta. Now, if our structure is regular, then it is easy to see that this value will be 1. Therefore, the energy of any vertex that is greater than is equal to 1. If we add them all, we get the energy of a t-gain graph phi, which is greater than is equal to the number of vertices. And equality occurs if and only if phi switching equivalent to a balanced complete bipartite graph together with the same partition size. So the corresponding results for undirected graph is known in the literature. Well, now here we discuss energy bound in terms of vertex Covan number. Wang and Ma 2017, they proved that for a simple graph G, the energy of G is always greater than is equal to 2 times vertex Covan number of G minus 2 times the number of odd cycles. And they characterize the equality. Later, Wei and Li, they extend these results for mixed graph. And here, it is possible to extend these results for T-gain graph. So the energy of phi, which is greater than is equal to 2 times tau of G minus 2 times C. And equality occurs if and only if each component of phi is balanced complete bipartite T-gain graph with perfect matching together with some isolated vertices. Now the next, energy lower bound in terms of minimum vertex degree. So Ma in 2019 proved that for connected simple graph G, energy of G is always greater than is equal to 2 times smallest vertex degree of G, 2 times small delta, smallest vertex degree of G, and characterize the equality. Now the question is it possible to extend these results for arbitrary connected T-gain graph? So the result need not be true for arbitrary connected T-gain graph. Here is the example. So in this example, we can see we take a triangle, okay, and the gain of its all edges in a particular orientation is iota. Then its energy is strictly less than 2 times the smallest vertex degree. Okay. However, we can establish the result for triangle phi connected T-gain graph. So here is the result. Let phi be a connected triangle phi T-gain graph. Then the energy of phi is greater than is equal to 2 times smallest vertex degree. And equality occurs if and only phi is switching equivalent to complete balanced bipartite graph together with the same partition size. Okay, so the sketch of the proof. So we will prove this with the help of bounds of energy bounds of its each vertices. Okay, so one of the key result, let phi be a connected T-gain graph with at least one edge. Then the energy of its vertex Vi is greater than is equal to the degree of the vertex Vi times the spectral radius of its underlying graph G. And equality occurs if and only phi is balanced and G is complete bipartite. Well, now, as we know that the energy of a T-gain graph phi that can be represented as the sum of its vertex energy. So, and then from the above result, we see that this is greater than is equal to sum of the degree of the vertex Vj divided by spectral radius of G. So, which is again greater than equals to n times the smallest vertex degree by rho. And now, there is a known result that the spectral radius of G means underlying graph, which is less than is equal to the square root of the number of edges. And now from Mantel's theorem, we know as it is a triangle phi graph. So this is greater than is equal to n times delta into square root of floor of n square by 4. And from there we get it is 2 times small delta. Now look into the equality part. So if energy of phi is equal to 2 times small delta, then all the intermediate inequality will be equal. So from first inequality, if this is equal, then from there we get from our lemma that phi is switching equivalent to a complete bipartite graph, a balanced complete bipartite graph with partition size A and B. Let's say A and B. Now from the equality of second inequality part, from there we get G is regular. And from this section we get G is a complete bipartite graph, and by Mendel's theorem we get, and also from this inequality, this equality we get, G is a complete bipartite graph together with same partition size. And combining all, we get the result. Means equality occurs if and only if this is switching equivalent to that. Okay. Now, energy upper bound in terms of vertex cover number. Wang and Ma, they proved for a simple graph G, the energy of G means a simple graph G, this is less than or equal to 2 times tau into square root of delta. Later, Wei and Li proved these results for mixed graph X, and he posed one open problem that characterize all mixed graph X for which equality occurs. So our next results is about to prove the equality for a bigger class of graphs, T-gain graph. So this is the result. So energy of a T-gain graph phi is less than or equal to this, and equality occurs if and only if phi is disjoint union of tau G copies of balanced T-gain graph, okay, together with some isolated vertices. Let's sketch up the proof. So G, this is a underlining graph G. So we take a T-gain graph phi on this G, and U be a minimum vertex cover of G. Suppose we take X is a member of U, and S is a this is a induced subgraph after removing the vertex X. Okay. Then we can see tau of G is nothing but 1 plus tau of S. Now, the adjacency matrix of a T-gain graph on this underlining structure G, that can be expressed as the sum of the adjacency matrix of this part plus the sum of the adjacency matrix of that part, right? Therefore, from there we know the energy of phi is less than or equal to the energy of the star plus the energy of this portion S. Okay. So here we use the induction. So as we know that the energy of the star with d number of pendant vertices. So here we say the degree of this X is d. So which is nothing but 2 times square root of d, and plus here we use the induction. So 2 times tau s into square root of delta s. And after a sort of calculation, we can see that this will be nothing but 2 times tau of g into square root of delta g. Okay. Now, for the case of equality, so here we have a few more parts. So first, we are going to prove that all the vertices of U are of degree delta of G. Okay. And then we will prove that each component of this T-gain graph phi, each component of this T-gain graph phi is balanced, is bipartite T-gain graph. Okay. And then we'll prove that, then we'll obtain that each component of G has exactly one positive eigenvalue. So previously we have seen that if our structure is bipartite and it has exactly one positive eigenvalue, then that means our T-gain graph phi is a balanced complete bipartite graph, okay, with partition size A and B. Okay. And finally, using some calculation, we can show that A is 1, and the size of one partition is 1, and the cardinality of another partition is delta of G. And that will give us the result. Okay. So now the gain distance matrices. So here we will introduce the notion of gain distance matrices for T-gain graph, and I'll present some of their properties. Well, so recently Hamid et al. They introduced the sign distance matrices for sine graph, and a gain distance matrices of a gain graph that will generalize the sign distance matrices of sine graph as well as the distance matrices of ordinary graph. Okay, some notation. Let phi be a connected T-gain graph Suppose S and T be two vertex from the vertex set of G. Now consider SPT as an oriented path from the vertex S to T. And we define PST, that is the collections of all shortest path from S to T. Now here we define one ordered vertex set. So V of G together with one ordering we are taking. So that is a total ordering of the vertices of G. So suppose V of G, this is the vertex and its vertices are labeled by V1 up to Vn. Then an ordering less than R is called the reverse ordering of some ordering less if Vi less R Vj, if and only Vj less than Vi for any I and j. Now, an ordering less than is, we use this as a standard vertex ordering if the vertices obey this ordering, V1 less than V2 up to less than Vn. Well, let phi be a connected T-gain graph with an ordered vertex set V of G, less. Then we define a maximum auxiliary gain. Okay, then we define two auxiliary gain. One is maximum auxiliary gain, another is minimum auxiliary gain of a T-gain graph phi with respect to the ordering less than. Okay, this is a mapping. It is denoted by phi max less. It is from V cross V to T, defined as follows. So for any two vertices S, okay, phi max less S, S, this value is 0. Whenever two vertices S and T, S is less than T, then we take phi max less S, T. This is nothing but the maximum gain over all shortest path from S to T. So this maximum is taken with respect to lexicographic ordering of complex number. Okay, because this is a complex number, right? And further, in that time, phi max less T, S, which is nothing but the complex conjugate of phi max S, T. Okay. So similarly, we can define minimum auxiliary gain function phi min less S, T. So that phi min less S, T. So whenever S less than T, that time phi min less S, T, that would be nothing but the minimum gain over all shortest path from S to T. Okay. And this minimum is taken with respect to lexicographic ordering of complex numbers. And this time, similarly, phi min less TS, that would be nothing but the complex conjugate of phi min less ST. Well, now here we define so here we define two types of distances. One is maximum gain distance, another is minimum gain distance. Okay. So maximum gain distance is nothing but the product of the auxiliary, is nothing but the auxiliary gain is nothing but the auxiliary gain function times the usual distance between the vertices S and T. And similarly for minimum.
Excuse me, Aniruddha, you have about like 3 minutes left.
Okay, sorry.
You have about 3 minutes left.
Okay. Sorry. So and gain distance matrices is what? So they are the Hermitian matrices, right? And its ijth entity is nothing but the its ijth entity is nothing but the gain distances from the vertex Vi to Vj, and similarly for d min. Okay, so this is one example. So here we are taking, this is the, here we are taking the standard vertex ordering and they are the leveling of the vertices. Then D max less, okay. So the maximum distance matrices. So this is a, here we can see this is a Hermitian matrix. We can see from the figure. So similarly, we have the distance matrix with respect to the reverse ordering with reverse ordering of standard vertex ordering. Right. So we can see the maximum distance matrix is different with respect to standard vertex ordering as well as the reverse of the standard vertex ordering. Even their spectrum are also different. So here we are defining vertex ordering independent T-gain graph. So if D max is same with respect to standard vertex ordering and the reverse vertex ordering, and D min is same with respect to standard vertex ordering and the reverse vertex ordering. Okay. And in that case, their equal matrices is denoted by D max phi, and their equal matrices is denoted by D min phi. Sorry, Tina, how much time is left? I mean,
That's less a minute, like a minute. So
10 minutes?
No, 1 minute.
1 minute. Okay, okay.
Yeah,
Let
so
me finish. Anyways, just a minute and give me. I'll just anyways. So well, so these are, I mean, the distance compatible means if D max and D min are same with respect to the standard ordering, then their equal matrices is denoted by the distance matrix of phi. Okay. So this is the result, one of the result here. If phi is distance compatible, then, and if phi is switching equivalent to psi, then psi is distance compatible and they have the same spectrum. Well, so these are not so much important here. So let me just final result trying to see. Yeah, the characterization of distance compatible gain graph. So let phi be a bipartite T-gain graph, then phi is distance compatible if and only if phi is balanced. And here, the another characterization phi is, phi be a T-gain graph, then phi is distance compatible if and only if every block of phi is distance compatible. So these are the references. Yeah.
thank you.
Yeah. Yeah. Any question?
You mentioned the that you've got this uncountable class of graphs, and I'm wondering if you have, for any particular base graph, a class of uncountably many examples, or some situation in which you have more exotic gains than roots of unity going on that are giving you something that looks more fundamentally continuous in some sense.
That I have to, I have to see this, because I have just started working on this field. So there are a lot of things I have to explore. I mean, the main fact is that right now, we are just working with the 0-1 matrices and all. And now we, from a real setup to, we are going into the complex setup. Okay. So that's why you are starting from the complex unit gain graph, means the unit circle. Okay. So there are many things to explore. And so that I'll see.
Yeah.